Good afternoon. Thank you all for coming. I'm here with Tim and Simon to talk about the work that has been happening around Julia and GPUs. I'm going to talk first about the general Julia GPU ecosystem, just giving you a short overview, a slight dive into OpenCL.jl, and then Tim is going to take over and is going to talk about the Julia CUDA compiler, and then Simon is going to talk about a higher level package called GPUArrays that brings all these different worlds that we're going to touch upon together. If all works well, you should be able to go to GPU.JuliaBox.com, and it might take some time, but it should give you an JuliaBox instance with a GPU enabled, and all the GPU packages are pre-installed, and hopefully, if we don't crash the system, you should all be able to do especially the later exercises and start working on examples. But for me, it's still timing out. So let's hope that it works. Perfect. Okay. The slides and the IPython notebooks, these slides are based upon are available at the following links. And as I mentioned, we are going to talk about why are we actually interested in GPUs and why do we want to bring Julia to GPUs. And then the broad overviews of the different possibilities of working with GPUs in Julia. I'm going to talk about how to work with the APIs. The two big APIs are OpenCL.jl and CUDA. And then I'm going to do a quick example of how you would use some of these tools to, as an example, calculate an FFT on a GPU. And then I'm going to hand over to Simon and Tim. So, first of all, just a quick question to the audience. How many of you have worked with GPUs? Okay. How many of you have worked with CUDA? How many of you have worked with OpenCL? Okay. So for all of you who actually know what GPUs are, this part is not going to be as interesting. But for the rest of the audience, GPUs are massively parallel machines, and we have them in almost every computer nowadays. Your laptop has one, your desktop at home has one, and most likely the data center next to you also has one. They were initially developed for rendering of graphics-intensive applications. So if you look into the history of GPUs, they were designed for CAD work, computer-aided design, and later on for games. When the requirements for these applications got more and more intense, though the programming of these GPUs got more and more complex, and more control was handed over to the programmer. If you think about how you would tackle such a problem, the solution that GPUs provide is quite ingenious. You want to do an operation per pixel, right? You want to render an output, and so if your display is 1080p, you have so many pixels that you need to generate values for, and you have to do that for each pixel. And if you just do that in serial, your latencies between image frames will be too short. So you have to do that in parallel. And so GPUs are single instruction, multiple data machines, SIMD machines. And as I said, they're highly performant for certain tasks like rendering like numerical simulations where you have the same constraints, and they are available in many desktops and nowadays HPC platforms because they provide such a big performance advantage over traditional CPUs. This picture is from a current day NVIDIA GPU. I think it's a GP104, which is a 1080 of the current generation. And all the green blocks you're seeing are CUDA cores, semi-independent computational units. They don't operate completely independent, but all of these can do operations at the same time. And everything that's blue is memory. And you see the memory hierarchy here is actually quite complex, and you need to take it into account once you start to write low-level GPU code. So before we had general purpose GPU computing, there was just GPUs, and they were only used through shaders. And these shaders were very much designed and developed for graphical applications. And in about 2003, between 2001 and 2003, people realized that they could reuse these shaders to actually solve different tasks. And they started doing numerical simulations of physical properties. And in 2003, there was the POC language was developed, which translated C-like code into DirectX or OpenGL shader. And then you could run the shader through your graphics pipeline, and you would get a numerical output at the end. In 2006, NVIDIA realized the potential that this general purpose programming of GPUs could have, and they released CUDA. And in 2009, there was the initial release of OpenCL on the Apple platforms back then as an alternative to CUDA by an open standards committee. GPUs are good for image processing, naturally. It's quite natural to write image processing algorithms. Nowadays, they're used heavily for convolutional deep learning. So the entire deep learning hype is possible due to GPUs. Also Bitcoin mining is quite popular to do on GPUs. And then most matrix operations, like most numerical code that relies heavily on matrix operations, can be made a lot faster by exploiting GPUs. Fast Fourier transform is another example. And there are many more, but there's also the other side of the coin where you ask yourself, what is a GPU not good at? Because there is no such thing as a free lunch. If GPUs would be the end-all to every problem, we would just use them as everyday platforms, which we can't. One of the problems is that there's a memory transfer bottleneck between the host device, so your computer, and GPUs. And so every time you want to move data from your current program to the GPU, you have to go through a fairly slow PCI bus. And that memory transfer cost, that latency, can negate any and all benefits that the acceleration might have. So in most cases, once you start porting up application, it can be advisable to completely go to GPUs and even do inefficient things on the GPUs just to not have to deal with the memory transfer cost. Then, of course, the programs actually need to fit the programming model, which is not our traditional one that we are used to for writing CPU code. Then there's no magic silver bullet that just makes the code faster, even though several people are trying to sell you some. They all have downsides, and they all require you actually to restructure your code so that you can exploit parallelism. Memory on a GPU is limited. So in a best case scenario, you currently have 24 gigabytes of memory on a GPU. These are the most expensive ones, and in like consumer applications, you will deal with 2 to 8 gigabytes of memory. And if you compare that to a high-powered workstation, where you can go up to hundreds of gigabytes of memory nowadays without breaking the bank, that is quite a difference in able to like reasonably work with big data sets. Also, the cost of moving data to a hard disk is less on a CPU than it is on a GPU, because on a GPU you lose a lot of the benefits by having to do the transfer from into the hard disk. So you don't want to do that, but then your data set is also maybe smaller. And one of those other problems, those little gotchas, is the specific architecture of the GPU will constrain how you can write efficient code. And as most of us will know, branching on a CPU, unpredictable branching on a CPU costs a lot. If you can predict the branches, it's fine. But it's actually worse on a GPU, because a certain number of cores will operate in lockstep. And if one of them breaks out of lockstep because it needs to take a different branch, your warp will execute one side of the branch, and then it will execute the other side of the branch, and then it will merge both results. So you do twice the work always if you have a branch on a GPU. So, how can we work with GPUs in Julia? And in the GPU world, there are several APIs on the driver side that allow us to interface with these devices. And there's OpenCL, and there's NVIDIA's CUDA. And for my little quiz in the beginning of the talk, a lot of you are more familiar with CUDA, and that is because NVIDIA has been more effective in bringing CUDA into the academic environment and getting people to use it. OpenCL has the benefit that it can run on any device. It can also run on a CPU. It can run on your ARM phone. It can run on AMD's and NVIDIA's graphics card. So it's a lot more flexible if you already know that you're going to move your application. But if you're working in a cluster environment and it has NVIDIA GPUs, you will want to use CUDA just to take the most out of the system. We support all of these APIs, and we have packages under the JuliaGPU organization. And in the next couple of minutes, I'm going to use OpenCL.jl, first of all, because I'm more familiar with it, and second of all, because it can run on a laptop. And yeah. So just to give you like a small feeling of how it is to write OpenCL code in Julia, we start out with importing the package. Then we create a device, a context, and a queue. All of these three things are OpenCL concepts, where the device is the actual computational device. The queue is used for synchronization, and the context is for memory management. Then we will create a kernel, a program that will run on the GPU. And in this case, we have to write it in C, in OpenCL C. You see these annotations to the input variables of the function. There's also a kernel annotation that tells the compiler this is a kernel function. And then we have global address space for memory that is global on the GPU. And then we need to get an ID which references our current work element that this one core on the GPU will work on. So the code has a perspective of that single core, and you will need to reason based on those IDs. And then we just do our simple operation. In this case, we just want to add 2 vectors and store the output in another one. Then we need to compile that program, and we will create a program, we will build it, and then we will get a handle for the individual kernel that is in this program. So you could, in this code, have 30 kernels and then get handles back to each one of them. Then we now define our problem size, and so I said, okay, 500,000 sounds like a good problem size. We create input arrays, and then we need to use these Julia arrays to create GPU arrays, so arrays that live on GPU memory. And in OpenCL, we pass on, these are called buffers, and they have an element type, they have a context that they live with, and then you can say, wait, this is a read-only buffer for the GPU, which is backed by a host buffer, or this is a white buffer that can then be written to at the GPU level. And then you just queue up the kernel with the work size of A, and you pass along the arguments to that kernel, and then you read back the result. And in the ideal case, the results between the two operations should be the same. One topic I wanted to touch upon before handing off, so this is how you would write an OpenCL program, and if you want to write a CUDA program, it looks very similar. The terms are different, and the code looks a little bit different, but the general idea is you have to provide a C program to then compile, execute on the GPU. You probably only want to interact on that level if you already have code like that from a prior project that you want to run in Julia to then use Julia to do further data processing. And so if you want to benchmark if GPUs actually bring you benefits, you need to be careful because you need to take into account the time it takes to transfer data, the time it actually takes to execute the kernel. The kernel will execute in most cases asynchronously. And so you need to time the right things and make sure that your benchmarks are actually meaningful and that can be non-trivial. So if you see benchmarks where GPU code is a factor by 10,000 times faster than CPU code, the benchmarking probably was done poorly. It should be faster, but it should not blow you out of the water. And in OpenCL.jl, currently a lot of operations actually do block, and so the benchmarking works fairly straightforward. I thought in the beginning that it didn't block and had a quite elaborate example written where I benchmarked all the data transfers, but it didn't make a huge difference to the runtime because the main call already blocks and the operation runs. And here you see, so this is only executed on my laptop. If I write the same operation in native Julia code, surprisingly it's actually faster because we don't have the overhead to deal with. And this is just running on my local computer. If I would now have a dedicated GPU, then once I scale up to problem sizes where the memory transfer cost is naturally you will start seeing performance benefits. And also the problem size needs to be big enough. If you don't want to write your own programs, there are a couple of libraries available, Q+, QFFT, CL+, CLFFT, that will allow you to do most common operations directly. And as an example here, let's calculate an FFT, and I just import CLFFT, and then I create a buffer on the GPU, and I create a plan, I tell it what layout my data will have, and I then enqueue that transform and read the result back. It's a little bit more complicated than to work with the FFT library in Julia, but it allows you to get started right away instead of to have your own code. For me, my journey into Julia has started with working on OpenCL.jl, and I'm quite thankful for the warm welcome I got about 3.5 years ago. And these are all of the main contributors to the JuliaGPU organization. and we are trying together to build a solid infrastructure that users can use, and contributions are almost always welcome. Now, we originally planned, I originally thought we would do this differently, but I would like to welcome Tim to the stage so that he can talk about CUDAnative and our recent efforts to build a native CUDA compiler in Julia.
Must be the other way around, I guess. Okay. Okay, do you hear me? Welcome everybody. I'm going to talk about CUDAnative, which is a... in the big microphone?
Yes.
Okay, will do. So today I'm going to talk about CUDAnative, which is our recent effort to bring a native compiler to Julia, allowing to write GPU code for CUDA NVIDIA GPUs in Julia itself. As you might have noticed, I have prepared both a talk and a workshop. Today the workshop is going to be hands-on in a way. I'm going to show a lot of code. I'm going to assume that you have some experience with GPU programming already. The talk tomorrow is going to offer a more high-level point of view in which I'm going to assume less knowledge and going to more show how everything works and what the future is and how it's built and so on. But for now, I'm going to be showing a lot of code which you can follow along on these links, which I've also posted on the Slack. All of this is going to be a pre-rendered Jupyter notebook because I do not trust the network of doing this live on a system which has a GPU, because ironically my laptop does not. So first of all, what is CUDAnative? CUDAnative.jl aims to be a replacement for CUDA-C, which means that you can use it to do low-level GPU programming using low-level abstractions. But conversely, that also means that you need to have quite some knowledge about programming GPUs. You need to know how to tap into the parallel architecture that is a GPU, and we do not aim to make it fun and to make it accessible for people without any experience. That's where other packages like Simon's JPUArrays.jl comes in, which in turn can be built on top of infrastructure like CUDAnatives. It is also, in a way, a work in progress. With respect to Julia, that means that we do not support all of the language. There's quite some restrictions actually, but kernels tend to be simple, so it doesn't hurt as much. More on that in the talk tomorrow. And with respect to CUDA, we also do not support some functionality, the biggest ones being atomics and dynamic parallelism, but both of which we are obviously still working on improving that. The talk today, I'm going to start with some explanation on what the requirements are to install CUDAnative. I'm going to explain how to install it, and next I'm going to shortly describe the programming model, which Valentin has also been describing already. Next, the gist of the talk is going to be how to use CUDAnative, how to analyze the performance, how to optimize it, and lastly, how to debug any issues which you can run into. So first of all, the requirements. Currently, we only do support Linux, even though it probably does work on a Mac as well. We do not have a CI system set up, so we cannot reasonably support a system we cannot automatically test our code on. We currently also, yes? Who's managing is the mic working?
No, the mic went out.
Oh.
I don't know why.
Who's managing the talk in the back? Anybody? Yeah, the mic's still on. It's still connected. Nope. Can you?
There we go.
This one as well?
No, this is that.
So this one works?
Yeah.
All right, let's use this. What was I saying? Yeah, so we only support Linux and we only support the current stable branch of Julia. But again, 07 support, it's supposed to work, but it's sometimes a bit hard to keep up with master. For example, the current Julia master is broken because of the recent changes on GC passes. But in general, we try to keep up with master. We also only support somewhat recent NVIDIA GPUs, namely the ones with shader model 2.0 or more recent. But for all practical intents, most of you should have a GPU like that if you're dealing with CUDA code already. Next up, installation. There's two main dependencies, one being CUDADriver.jl, which is simple to install, the other one being LLVM.jl, which sadly for now requires you to have a source build of Julia. We do not support binary distributions, so you'll have to check out Julia from scratch, which luckily only consists of 5 lines of instruction, but can easily take up to an hour. That's why we had hoped to have the JuliaBox working, but as it turns out, it seems quite finicky and most of you cannot connect, I guess. Anyway, so if you would want to run this on your own system, compile Julia from source, make sure you're compiling the latest 0.6 release or the release branch, and you should be set to go. Afterwards, you can just pkg add CUDAnative. If any of you manage to log in on the JuliaBox, you can just run this command and get a working CUDAnative setup straight away. For these slides are rendered on a system where I'm running Julia 06 with LLVM 3.9 on a 64-bit Linux system with the NVIDIA driver 375 and CUDA 7.5, in case it would matter for benchmarks results and so on. And I'm using a GeForce GTX Titan on a 377K Intel CPU. In short, the programming model, because Valentin has already explained it in some detail, it's a single program, multiple data, SPMD programming model, in which you write a single program which, what's in the name, processes multi-data elements. This is very comparable to SIMD, but has some differences in that not every thread has to execute in lockstep, as is the case with SIMD. If we would want to emulate this programming model in Julia, you would have some hypothetical execute wrapper, which takes a kernel function, an amount of threads, and a certain amount of arguments. And every thread is then going to run the kernel for said arguments, defining some hypothetical thread variable kernels can access. Say you can write a kernel which is going to perform a vector addition, adding B and A into C. Then we can allocate some data, execute the kernel, and we get the results we expect. Conceptually, this is of course very simple, but real-life GPU implementations have quite some additional complexity. One being, we're not dealing with threads and only threads. Threads are grouped in blocks which make up the grid, and we have different storage behavior and performance for different kinds of memories, with also the communication between threads and the synchronization different between whether the threads are part of a block, part of a group, part of a lane, and so on. So this is a lot of complexity, and again, CUDAnative.jl does not attempt to obviate that. So we are still programming at the same abstraction level as CUDA. We're just doing it from within Julia. So the interesting part is, how do we use CUDAnative.jl? Being a CUDA C replacement, it takes care of providing compiler intrinsics you need to write GPU code. It also provides compiler support, enabling the compilation of Julia code to PTX, which is the assembly format used for NVIDIA GPUs. And it also offers some level of language integration to make it easy to call GPU functions from the CPU. However, at the same time, you still need another library to manually interact with the CUDA APIs. For example, to manage your device, to manage operation, to allocate arrays, and to handle the execution context. You can use different packages for that. We have developed CUDADriver.jl to be used within CUDAnative, but there's also Tim Holy's CUDART.jl, which mostly offers the same functionality but based on the slightly higher level CUDA runtime API. So how would this look? We would obviously start by importing the necessary packages. In this case, I'm using CUDA driver for the API interactions because that's what I have most experience with. You start with getting a hold of device handle, and next you instantiate a execution context, which will wrap all of the resources you are currently allocating. That means that at the end of the program, you'll have to destroy this context for these resources to be destroyed. And you can also use a do block syntax to do all this automatically. For the rest of the workshop, we'll be allocating a single context, which I will be using for all of the examples. So one thing that Valentin also mentioned is that we probably will use some extraction of GPU arrays. We have developed one in the CUDADriver.jl, which tries to mimic most operations supported on the base array type. So you can allocate it with the convenient constructors you're used to. You can allocate it with some data on the CPU, and you can fetch back data easily. For example, we can allocate a QArray with 2 items of type integer, which yields us an uninitialized array. However, we cannot do indexing because in the end, this is still a GPU array which lives in the GPU's memory space, so we do not want to offer you the illusion that you can just access data cheaply. However, we can easily fetch it back to a CPU array, at which point you can obviously modify it like you want. And we can easily pass this to kernels, at which point the @CUDA macro will do all the magic. But more details on that later. One interesting property of the QArray we developed is that it's fully garbage collected. Say we want to inspect the current memory usage of the GPU, the mem subpackage is also part of CUDA driver. We currently see that on a brand new context there's 72 megabytes allocated. If we allocate an array of a couple of elements which would take 80 megabytes, we can clearly see that the usage of the memory on the GPU increases by around 80 megabytes. However, say we forcibly finalize the array, which the garbage collector would do when the object goes out of scope, we see that the memory usage on the GPU drops back to what it was before. However, the memory pressure of the GPU currently is not communicated with what the JuliaGC uses as a metric for memory pressure. That means that if you're allocating a lot of arrays when they go out of scope, the JuliaGC might not kick in and you might end up with error out of memory. At that point, you might want to insert some manual GC calls, and if your array has effectively gone out of scope, it will be collected and the memory will be freed. However, now for a more basic example which shows you how to execute code, I'm going to go with the vector addition because it's easy trivially to parallelize and it doesn't require any communication or synchronization between threads. So we would just start with writing a kernel function which takes 3 untyped parameters which will end up being arrays. We fetch our current thread index, which in the massively parallel execution model indicates which element we are responsible to process, and we finally just perform the addition of 2 elements. We're going to start with allocating some data on the CPU. We upload it to the GPU and we allocate a buffer for the output values. And then we perform the magical @CUDA call, which is going to lazily compile the kernel for GPU code and going to execute it asynchronously on the GPU. The first tuple argument is the launch configuration, which in this case indicates that we want a single block consisting of len threads, which means that we're going to have the exact amount of threads necessary to process our array. Do note that this call is asynchronous, but yeah, well, this actually corresponds with the call you're all familiar with in CUDA, where you have the triple angular bracket syntax to call functions. Next, if we fetch back our values, we synchronize the GPU, we download the memory, and we verify that the result is correct. Say, as an optimization or as a next step, you want to scale this up and use this algorithm for more threads. Say, in this case, an array of len 2048. Again, we upload our data, we upload our output buffer. However, calling @CUDA is going to fail. Why is that? Some of you might know. turns out we have a limit of the amount of threads we can allocate within a single block. This we can query for the current GPU and the current CUDA setup by using the attribute function, which is also part of CUDA driver. Even worse, then turns out we have restrictions according to every dimension. The mic died again, I guess. In the back, the mic. 1, 2, 3. Is there a third mic? Yeah. Then what about the video?
Video is different. Video is the one we have on there.
This one is for the video? Oh, okay. I'll just talk loudly then. Let me put this in case it works again in a while. So it turns out we have different limits for every dimension we're launching threads with. One way to cope this is adjust our kernel. We could, for example, instead of launching a single block consisting of an amount of threads, launch multiple blocks and compute our current index we have to process accordingly. So in this case, we're going to look at the current block ID, we're going to multiply it by the size of the block, and we're going to add the current thread ID. We have to check whether we're within bounds, because we could have possibly launched more threads, but finally we can just at this point calculate our launch configuration and launch the kernel as we did before. And this is going to yield the results we expected. Do also note that the launch configuration is three-dimensional, which can make it easier to implement your algorithm in terms when you're processing three-dimensional data. So one interesting thing you're all used to for programming Julia on the CPU is that you can reflect upon the generated code at every point. This is the same with CUDAnative. However, we override and implement our own functions for some of this. Why is that? Because we have a custom toolchain, a custom compiler, which means that we're not relying on base code gen to generate our LLVM IR. Similarly, we're also defining custom macros, the code lowered, code warrant type, and all of the others, because it has to support the fact that you might have the @CUDA and a tuple stuck into there, which has to be removed from that. And we also do some type conversions when launching a kernel. For example, if you're calling a kernel with a CUArray as an argument, it's going to be implicitly converted to a CUDevice array, which offers similar functionality but for the device side code. So that means that if you just want to use @code LLVM, it's going to bail because you didn't specify whether you want to use the base code gen or the code gen in CUDAnative. So we do CUDAnative.code LLVM, and it's going to give you some nice looking LLVM code. Code PTX does not have to be specified because it's not part of base. If you do it, you get the PTX code you expect. And we also have code SAS, which gives you the shader assembly code, which is a very low-level code that's going to be executed on the GPU. For a less basic example, which shows some decent properties of the GPU, let's do reduction. For example, say we have this one works. Okay. So we're going to do a reduction across columns. Say we have an array of 3 rows and 4 columns. We want to reduce it according to the sum operation across columns. How would we implement this on the GPU? In order not to do this fully in serial, we are going to have a parallel algorithm which is going to logarithmically, at every iteration, drop off a certain of threads. I'm not going to do much in detail here because in the end I'm just wanting to show how the toolchain works. Tomorrow in the talk I'm going to give a proper description of how this parallel algorithm works. We also want a way to conveniently call this code from the CPU, which is going to accept a CPU matrix, upload it, perform the kernel, and download it back. Let's verify if this works, and it does. However, if we benchmark it, we see that the GPU code is surprisingly slower. How come? Well, Valentin already spoiled the answer. Turns out that there is a lot of memory overhead because of transferring the arguments. If we were to benchmark this on the GPU and only on the GPU by inserting CUDA events, as I do in here using CUDA driver.addElapse, which is similar to the base.addElapsed, but in this case it's going to insert the proper timing events in the GPU command queue. We can see that it only takes 0.34 milliseconds out of the 1.6 milliseconds it takes to run the entire algorithm, which means that there's a lot of overhead transferring arguments back and forth. So that's why it's always interesting to keep as much on the computation on the GPU as possible. However, even then, the algorithm that I've showed is extremely naive. It's not work efficient. It doesn't use any of the optimized memory hierarchies. You can optimize the way it loads from memory. There's a lot of stuff to do, but I'm not going to discuss this because this, in a sense, is knowing how to program a GPU. And what I want to discuss is how to use CUDAnative for programming GPUs and what the issues with that are. So how would you measure performance then? I'm going to talk about two kinds of performance. The first one is launch performance, because as you might know, it's crucial that you can queue kernels very fast without having any overhead. Say we use CUDAnative in a brand new environment, we define a kernel function and we launch it. It takes a whopping 8 seconds before our kernel returns. However, if you call it a second time, it only takes 36 microseconds. Where does that come from? Part of that is because the kernel has to be compiled brand new. Part of that is also because loading CUDAnative and loading all of the packages involved with that is pretty slow. So as you can see, the 36 microseconds is as fast as statically compiled CUDA-C, which makes it possible to very fast queue kernels without any additional overhead, and that's the important part. However, even if in this non-clean session we would define a second kernel and launch it, it would only take 100 milliseconds, which means that a lot of those initial 8 seconds comes from inferring and compiling CUDAnative, CUDADriver, LLVM.jl, and all of the packages involved. The second important metric of performance is how the kernels themselves actually perform. At Ghent University, we've been working on porting certain benchmarks from the Rodinia benchmark suite, which is a benchmark suite that focuses on heterogeneous kernels. And as you can see, in general, we have around no performance difference with except for some outliers. One of the outliers being the leukocyte benchmark, because we do not support all of the memory types it's used, and the NN one, which is strangely a lot faster, but I haven't had time to look into that. But in general, it's possible to write code that is as fast as C, and you can queue it as fast as you would in CUDA-C. And those two are the big important features when you want to use a GPU as efficiently as possible. However, you have to program carefully. If you very naively write Julia code, you might run into some performance difficulties. One is if you want to pass non-is-bits types. So is-bits types are plain types which can be represented by a bunch of bits, so to speak. And sometimes some types like structs are not. For example, say we allocate a device array and we pass it to a kernel which just sets it to 0. If we would benchmark this, we can see I wrote a small function here, kernel benchmark, which is going to do the same as I described before, using events in the command queue to ignore the memory transfer, but just measure the execution time. It's 50 microseconds. However, what's going to happen behind the scenes here is because the argument, DA, is not in its bits types, we're going to pass this by pointer. That's the calling convention of Julia functions. As a result, this will have to do a memory allocation and a memory copy at the point that the kernel is launched, which obviously incurs quite a bit of overhead. If conversely we would pass this array first by pointer and then by length, both of which are is-bits types, the performance increases to only 4.6 microseconds. So if you write kernels in CUDAnative, it is important that you deconstruct non-is-bits arguments to their core bits types. However, of course, in the future we expect to be able to solve this and avoid having to jump through these hoops, but for now it's required. Another issue you might run into is that some types in Julia, when written as plain literals, they might end up being too wide for a GPU to handle efficiently. Say we write this dummy kernel, which is going to take the square root of an element multiplied by 2. If we would look at the PTX code, it's abbreviated because it's a bit long, you would see that there's some conversion operations in there. For example, you have the cvt.f64 instructions, and afterwards you have the conversion from 64 to 32 bits back. And this is because the 2.0 in Julia is a float64 literal. However, so this is going to result in quite a slow kernel, because having to allocate both 32 and 64-bit register is going to increase our register pressure, and as a result probably lower the possible occupancy. But it's also going to result in slower operations. For example, the square root function, if it's executed in 64-bit mode, is going to be a lot slower, especially on consumer GPUs, in which it can be up to 60 times or more slower when you use 64-bit floating point literals rather than 32-bit floating points. So if we would write our kernel like this, in which we query the element type of the array and instantiate the value 2 accordingly, and we again check the PTX code, all of the conversions have disappeared, and the square root is going to be executed in the 32-bit floating point domain. The problem with this is that Julia base currently does not always care about the precision of literals, especially with respect to integers. Oftentimes either small integers are promoted to regular machine width integers, or literals like a 1 are used in the code base, which again result in a 64-bit 1 being added into your GPU code. However, this is mostly an issue with floating points. Integer 64-bit types are not that much slower on the GPU. So of course, one important thing is how would you measure the performance of Julia GPU code being executed. And the good news here is that we can just use the existing NVIDIA tools. We can just use MVProf or MVVP to measure the performance. We even get, if you can see this, source code annotation based on Julia code and the resulting SAS code if you enable PC sampling on a sufficiently modern NVIDIA GPU. We also have CUDADriver.addProfile. However, this doesn't really profile, it's just going to activate the CUDA profiler around that code block, which makes it possible to have really narrow timeline views and is much more convenient to look at. Similarly, we also have CUDANative.addProfile, which is going to enable the NVIDIA profiler upon first kernel launch, which means that those initial 8 seconds it takes to load all of the packages and compile the kernel and load the kernel are not going to be included in your timeline view, but only the very narrow scope execution of the kernel. For debugging, again, as we can use NVIDIA tools for profiling, we can also use NVIDIA tools for debugging. For example, you can use CUDA-memcheck to do checking of out-of-bounds errors. Currently, we do not support proper out-of-bounds exceptions. The GPU is just going to trap when an exception occurs, but because of bugs in the PTX assembler, we currently do not do that for out-of-bounds accesses, which would be expensive anyway. So you can use tools like CUDA-memcheck to check for out-of-bounds accesses. You can also use CUDA-GDB to debug code. For example, say we use CUDA-GDB for the same out-of-bounds example, which is part of the CUDAnative.jl repository. We can break on our kernel by doing the setCUDA break on launch application. We can do a backtrace, and we can even look at a code view. However, the LLVM backend for PTX, called MVPTX, does not currently support emitting proper debug information, which means that we cannot access local variables, we cannot access the function arguments, or do other convenience printing functions. What we can do, however, is, as I mentioned with the profiling, we can do the source code linking of source lines to SAS assembly. So if you do in CUDA-GDB a layout split, you just get to see the Julia source code and the corresponding SAS code, at which point you can guess what code does and obviously print the value of registers, which can be a big help in debugging. What we do not support, as I mentioned, is all of the CUDA language. And if you use some of these functions, you might get some exceptions. For example, kernels do not support returning values, which will be nicely reported when you try to launch a kernel which returns a value. You have to return by means of output arguments. We also do not support certain language functions like calling into the runtime. For example, if we want to return an int array behind the scenes, that would have to do a garbage collection, and this would, if you look at the code type, result in a C call to JLalloc array 1D, which is not supported, and you would get a mention like that when you try to launch or compile a kernel which uses the runtime language feature. Sometimes, however, the call to a CPU library function can be hidden a bit. Say we want to call sign. The sign function is living in OpenLibM. However, the handle to that library is not opened by the C compiler. It is opened by dlopen into the base Julia library, which we cannot properly inspect. If we would launch this kernel, the driver would die. We would get error launch failure on every call we would execute. That's also why we do not properly support exceptions, because throwing a trap which would result in a launch failure is deadly. We cannot escape from it, we cannot reset the context, we cannot bail out of this situation. If you would look at the LLVM code, you will be able to spot this by the int to pointer instruction, which is going to be a pointer casted to a function handle, which would then be called by LLVM. And this typically points to CPU code being called from GPU code. So if you would ever in a GPU function get a launch failure and you look at the LLVM code and you spot an into pointer, you'll probably be using a CPU function which the GPU obviously does not support. So then the question is, how do we compute a sign? For now, we have to prefix many math functions using the CUDAnative.namespace, which would then result into a call to the proper intrinsics nv-synf, which lives in the libdevice GPU function. If you want to debug other failures, both CUDA-driver, LLVM, and CUDA-native support multiple output modes. If you run Julia with the environment variable debug equals 1, do note that you have to run with compile cache equals no, because otherwise the value of this environment variable is not going to be read. You get to see all of the information that's happening behind the scene, part of which might be interesting, namely that's the JIT info log, which also lists how many registers are being used for every kernel, how many spills have been allocated, which might help you into optimizing certain kernels for high performance. If you run with trace equals 1, you even get to see every API call, which might help you debug failures in whatever's being run behind the scenes. Okay, that's it for now. So I hope with this introduction you can have a start with running code on your GPU using CUDA-native. These are pointers to all of the 3 core packages that are being used. And as I said, tomorrow I'm going to give more of a high-level talk on CUDA-native. Again, how GPU parallelism works, how you optimize for it, with some more overview on CUDA-native, how it works, how it uses LLVM.jl, how it compiles using the existing JIT infrastructure. And on Thursday, I'm going to give a lightning talk on LLVM.jl, how you can use it to create your own compiler or to compile your own code and plug it back into Julia. All right, and now I'm going to give the mic to Simon.
Okay, this looks good. Hello everyone. I'm going to talk about GPU arrays, which I created on top of CUDAnative and OpenCL.jl and some other GPU packages. Its purpose is to get all these kind of different APIs together and have a nice layer on top of it to actually write code that doesn't rely on specific hardware or specific API. Because as you can see, for example, I don't have an NVIDIA GPU on my laptop, so I will never be able to install CUDAnative on this. I will never be able to run it on it. So code that only relies on CUDAnative will not run on my laptop. And I probably still want to demo it on my laptop. So GPU arrays makes a lot of sense in this way. And as Tim and Valentin already mentioned, some things are pretty complex in the GPU world, but it's relatively easy to give a nice abstraction over them. For example, figuring out the kernel dimensions that you want to call the kernel with. For simple cases, you can just have a good heuristic for that and be done with it. So you don't need to let the user take these choices. And as you can see, right now on my laptop I have 3 backends with GPU arrays. It's a pure Julia backend, which is multi-threaded. It's an OpenCL backend and, curiously enough, OpenGL backend. I will talk a little bit more about the OpenCL backend down my talk. The OpenGL backend is pretty interesting for myself. You probably know I'm working on GL Visualize and on graphics a lot, so I really want to have an array package that works nicely together with OpenGL. And this enables that for me. But I'm also trying to have OpenCL talk with OpenGL or CUDA talk with OpenGL, so that you can actually launch compute with CUDA or with OpenCL and then nicely visualize it as easily as possible. Or in the worst case, if none of the backends actually work with your hardware, that you still have a Julia backend to do the computations and still be able to visualize things. What I also have included in GPU arrays are the higher level GPU packages like CLBLAS or CLFFT, or equivalent would be the CUBLAS and CUFFT for CUDA, which offers BLAS and FFT functionality. And I try to make a very similar integration like in Base, where, for example, the multiply just directly calls to BLAS. And it actually works pretty nicely in Julia, because most of the routing from the star operator to the actual BLAS call is defined on the abstract array interface. So I can just intercept that with my GPU array code and only overload the very last instance where I actually call into the GPU implementation of BLAS. And I also try to have a nice array of constructors for GPU arrays. So you can just construct it from any Julia array. You have the similar function to create a similar GPU array, which will then run on the same context. And then I have broadcast implemented. And yeah, as I said, BLAS already. And the broadcast also works with user-defined function. And how I do that is I compile the user-defined functions with CUDAnative. Or for OpenCL and OpenGL, I've written a transpiler, actually. To be honest, I'm not a big fan of a transpiler. I mean, it takes the Julia AST, does transformations on it, and then prints out a string in C, OpenCL C code, which is pretty brittle. Like with every Julia version, it might just fail, or I will miss out on optimizations that come after the lowering part in Julia. and I would need to re-implement them in the transpiler. So I'm not a big fan of this approach, but it gives us good results for now. And it actually gave me the chance to develop some tools to work with a statically typed AST in Julia, which is needed, I think. So even if the transpiler will be replaced for OpenCL by something similar that Tim has been building for CUDA, I think there's still a lot of relevant work that we have in there. So I'm going to show you a bit of the API that I've created in GPUArray. So one of the most basic one is the GPU call, which calls a kernel on the GPU. So a Julia function on the GPU. You always need to pass it a GPU array as the first argument. It uses that to dispatch to the correct backend and extract the context, the GPU context, and on what GPU card it actually runs on. And then it figures out how to compile the Julia function for the correct backend, and then actually calls that. And this is cached, so when you call it 2 times, the first time it will compile it, the second time it will run the cached kernel. So I've implemented a very simple map here. And this is an interesting function as well. So you've seen in Tim's talk like all these functions to get the index of your current thread to index into the array. And what I'm doing here is I use the GPU array to dispatch onto the correct lower level function to actually get the correct array index. So that makes it a bit easier to write GPU kernels that run on different platforms. And then you can index into your array, run a function on it, and return nothing. It's the same restriction. Yes, and then it's actually even the same result as if you would run it on the CPU. What I have here is to show you a little bit how this works. I directly construct a CL function, which is kind of the lower level type I'm using to cache the OpenCL kernels. And it has the source field, which actually shows you the string that gets compiled, transpiled from the Julia function. So you see it actually goes through the dependencies and recursively compiles what's needed for the GPU kernel you want to run. And then you get, in the end, OpenCL C code, which I then can compile with the OpenCL compiler. And GPU call also works directly with C strings. That will obviously take away the ability to just run it on different hardware, because the C string needs to be for a certain backend like CUDA or OpenCL. But that makes it easy to just support legacy code that you still have as OpenCL or CUDA C. So I'm a big fan of doing these things in Julia. And the biggest reason is I get a lot of metaprogramming and a lot of nice functionality for free, which is very hard to get if you actually write this in C CUDA code or OpenCL code. And actually it allows me to almost completely reuse the same Julia code for all the different backends. So in theory, GPU arrays can be very lightweight because you just need to define a couple of primitives for every backend and then have a collection of Julia code that runs on every hardware. And that is what GPU arrays can use in the end to offer all the functionality like broadcast, like reduce, and all these kind of things. So I'm hoping for a very small code duplication, and it has been kind of working out. There are sadly a few differences still, which I couldn't eliminate yet. So the broadcast kernel is a bit different on CUDA than it is on OpenCL right now. But I'm hoping to eliminate that very. Yes? Question?
You're talking a lot about GPUs, but since you have OpenCL with this, you can also, is this able to use Xeon Phi Knights Landing as well?
Yes. So it's running wherever OpenCL would run. Yeah. And obviously CUDA and maybe even Julia the Julia backend wouldn't run there. Yeah. It's probably OpenCL has a larger scope than where Julia can run. So you could probably use it to run on FFPGA hardware as well. I haven't tried it, but in theory, OpenCL should support that. So I have a little example here about what I really like about Julia. So you can even write generated functions for GPU kernels, and for example, unroll this one for loop here. This is the Julia kernel. And you can also use complex, floats, and the operations on complex. It will actually use the functions defined in base and just compile them, so you don't have to specifically write them for the GPU. And this works pretty well for a lot of code that is already in base, because what you need to do for GPU code is it shouldn't allocate. It should, in the best case, work with immutables. And yeah, and a lot of code is already optimized in that way in base. So you can just use that. And as you can see, this works, and you get a nice Julia set image. And if you benchmark this, you will see that the difference is decent, but probably not as big as you want it to be. But I'm on my laptop on Linux. The support for having OpenCL run on the GPU is not that great, so it's probably not a big surprise that the speed up is not huge. I have another example which uses the Black Skull kernel. This is almost the perfect example for GPU acceleration, because it's per element on the array. It's kind of an expensive kernel to run per element, which makes it great. And it has a lot of small separate operations. So I expect the speed up to be much higher here. And I actually, in the end, get around 40 times faster code on the GPU, even on my laptop. So that's pretty nice. Yes. So I called what Tim called finalize is in GPUArrays free. This will actually dispatch for CUDAnative. It will dispatch to finalize. For OpenCL, it will dispatch to a similar function to free up the memory to work around the problem that the GC is not actually hooked up with the GPU memory. So it's not sensitive to the pressure. So you might actually need to call free in your code right now. It could be thinkable to write a higher level library on top of GPUArrays, which probably does something like Dagger. It could create a compute graph and then figure out where to put in freeze. But this is not the scope of GPUArrays. So we are slowly getting our abstractions in place. Yes? Question?
You had a loop like you had before with a bunch of different operations on the GPU array. When it transpiles it, does it just make like one big kernel that does all that, or does it make a bunch of separate kernels?
So the question is, if I have a kernel, if I just make one big kernel out of the function and its dependencies, or if I actually have a lot of smaller kernels and link them, I guess. So I'm not linking anything. I'm just doing one big kernel so far.
So how does it? Like, so if they're all contained within one for loop, then it's like it's obvious the whole kind of the loop is one kernel.
So what for loop?
You showed the Black-Scholes example, like, doesn't it?
Where's the for loop?
Oh, I see that. Never mind.
So the for loop is implicit basically because that's how the GPU model works.
So just this function just compiles one kernel.
Yes. So these are the GPU kernels which will get compiled with their dependency in one big file basically. And the rest here, they are just helper function to actually launch the kernel. So no need to compile them on the GPU, they will run in Julia. Yes, another question?
Maybe one way to ask this similar question is if you wrote the same Black-Scholes code, but instead of having the function be a scalar function, you
Yes.
have the function use like dot broadcast throughout, and then you called it without the dot, would that also work?
So if you have if you insert dots here, yeah, that would work and would be a lot more less performant. Because then, I mean, we have the dot fusion, right? And that would kick in, but as it's written right now, not everything would fuse. So you would have a couple of kernel calls, and that's always adding quite a bit of latency. But that's actually a good point. So the dot fusion is great for a GPU array package because we just get kernel fusion for free, which is a very important optimization to cut down on this kernel call latency. Yes, so any more questions about that? Great. I also implemented a bit more array-like functionality. It's just on a branch right now, so it's very recent. So I have a get index and set index implemented and even push. So you can just start pushing elements into a GPU array. If you should do that or not is a different question, but there are some good use cases for that. For example, if you have a large array and just want to update parts of it, the set index is a very important operation. Or sometimes you want to have a more flexible API for your user to just add new elements to an already bigger GPU array, then this might also work very well. I have the push use case quite a bit in my graphics code for people to just add new primitives to something that is already on the GPU, like instances, for example, that you want to render, or particles, just adding new particles. Yes?
Is there any particular reason that they're using float 32 instead of float 64?
Yes, because there's a big speed difference, especially on non-professional GPUs. As Tim said, it's between, I think professional ones are probably about 3-5 times slower. Twice? Okay, that's good. Well, that's great. But consumer could be 30 to even 60 times slower on float 64. Yes? Another question?
You mentioned the get index and set index implementations. So Julia has about 5-6 different versions of those things. You can index an array with another array or a boolean or range, etc. So how complete is your implementation?
It's not that complete. I just started. I'm trying to hook into the trade system that is in base as much as possible to recompute the indices, but that doesn't work out too well because it tries to route your calls in a way that it boils down to a single index operation. And if you just have single index operation, it gets very expensive for the GPU because then you need to schedule one single index operation probably 1 million times, which is a lot slower than batching this. So I try to, but at some point I just need to say, okay, I have a big array of indices. I just take this now directly and don't let Julia do the rest. Yeah, so right now I think it's just range indexing. For my own use case, I have rectangular indexing with a rectangle. But that's about it. I have one last example which I wanted to demonstrate because it also shows quite nicely what you can do with Julias and specializing on the type. So I offer vload, which is a vector load from an array. So it just loads 4 floats at a time, for example. And that works really nicely because I can actually pass around the vector type I want to load. And then it just figures out to what intrinsic this needs to compile down to. And this might give you good speedups. But actually, for this example, it doesn't at all. So regardless of if you call it with vec4 or loading a single float at a time, it's the same speed. And I guess that's because it's already perfectly vectorized in the normal kernel. So yes, that's it for me for now. Yes, a question?
Can you talk a bit about what you said in my use cases a few times? What sorts of things do you use this for in your own?
So I'm working with textures and using arrays to have, for example, for a height field or for particles. And if I want to update parts of the texture that I want to have a height field saved, and you can just do that. Or if you want to animate the surface, you can just update it with a set index, pretty much. Or yeah, or have a bunch of dynamic particles which die, or you add new particles, and then the push becomes very interesting. And actually, the text rendering I'm doing also runs on the GPU, which I'm not sure if that's a good idea, but so if you actually add new text to it, you directly write to a GPU buffer and just update that directly. So I actually also implemented splice and insert as part of the array interface. And the nice thing is I just boil it down to copy commands, so the code is completely shared between the backends. I think anything else would be a bit insane anyway, so yeah. Yes? Another question?
I'm not sure if this is a good question for now or later, but I'm just curious. So you mentioned you have multiple backends for different things. So my idea is if you were to, let's say, put data onto an NVIDIA GPU and use the CLFFT backend, what happens in that case? Does the CLFFT get run on the NVIDIA GPU, or is this something that gets copied to the CPU, runs there, and then goes back?
So the question was, if I have an NVIDIA GPU, but I guess not CUFFT installed, but CLFFT, what would happen? And I have a bit of a promotion going on, so I try to figure out a backend that works and then try to convert to it. But I just recently implemented that, so it's not covering a lot of cases. But in theory, I have the infrastructure set up to handle this in a decent way. This is especially important for the OpenGL backend because there's no GLFFT or GL BLAS. So it will definitely need to use the CLFFT implementation, and then it needs to figure out how to convert to that. Yeah, so I have pretty much a BLAS buffer convert trait which then dispatches on the backend, and the backend is just a function that figures out what backend is installed, and then I can overload that for OpenGL, for example. And for OpenGL, I just say if OpenCL CLFFT is installed, I just use that because that's probably the fastest one. And if that's not working, then CUFFT and after that I fail. Yes? No questions? Great. I have a question actually. So how many people of you have the full stack working on their laptop? The full Julia GPU stack? One person. That's 2. Did anyone try to install GPU arrays? Okay, a couple. Did it work out? No. Yes?
Yeah, it actually worked, and the intrinsic function seemed to be fine, like the dot plus, or if you broadcast anything.
Yeah?
But for some reason, it seems like CL plus isn't installed. Those libraries aren't. I'm not sure why.
Yeah, they're not in the best state.
Are they supposed to install automatically when installed on the computer?
Yes, but their build might fail if you're unlucky.
Yeah, that might. But the kernel part seems to be working.
The what?
The kernels that are transpiled.
That works fine?
Yeah, it's like when I was broadcasting things to GPUArrays.
Yeah, that's independent. I mean, that's completely my infrastructure. And then there's CLBLAS or CLFFT, which is just a library I bind in. And if that works.
Well, when you broadcast like sine or cosine, you call the intrinsic function on the device that it's supposed to?
Yeah. So for the transpiler, that's very easy. I just define the set of intrinsics and just stop compiling there. And for CUDAnative, it's a bit more complicated, as Tim pointed out. So we try to get rid of that, but how it is right now, that destroys a bit the ability to write code that runs on all hardware, even with GPU arrays. We had a hack, but that wasn't working very well. I think we can make it work, but we are not very motivated to put work into a hack. Because at some point we might just get compiler hooks to solve this in a nice way. Yes?
So about the installation, I'm assuming that we have to recompile Julia for GPU arrays.
We have what?
We have to recompile Julia
Precompile.
to make this work.
GPU arrays, the OpenCL stuff is easier to set up because that just works with the compiled binaries or whatever you have. It should actually even work with Julia 0.5, but I might have added code that relies on 0.6 in the newest GPU array version. Yeah, you just need to get CUDAnative installed, and that has exactly the restrictions that Tim talked about.
Okay. And is there any hope that this will ever work with the binaries in the future? Or
Yeah, there's hope. Just a bit awkward to set up, I think. Yeah, so I haven't mentioned that. So GPU arrays works in a way, at build time, it tries to figure out what package works and which doesn't, and it just does that by actually creating a context. And if that fails, it just doesn't add that back end. So if you added new packages after you install GPU arrays, you need to run build again. So that's probably what you ran into, that you installed CLFFT and couldn't get it to work.
Oh, you know, I think CLBLAS just had a build failure.
Okay, yeah.
I'm on OS X, so
Oh yeah. CLBLAS is a little bit finicky.
If you have a system with an NVIDIA GPU and you have the CUDA libraries and the OpenCL libraries, how do you specify which dispatch?
You can just initialize the backend explicitly, so you can just say like this.
Okay.
Yeah, and otherwise it will just try to get the best current backend that is installed. Yeah?
How about ARM-based hosts? I have a NVIDIA Jetson TX1 that has their GPU on it.
I think that works, right? But it's probably not tested. Is it tested? Nope. Okay.
So cross-platform support should work fine. I personally run most of my CUDA-native stuff on Power 8, and yeah, CUDA-native works great, and all the tools around it as well. So I think we have about another half an hour till we have to end the session, and I would say we are here for questions and answers if you have any more. We are also here if you have any troubles installing the toolset. And to those of a lucky few who got managed to get GPU.JuliaBox running and actually can write code to play around with it, we will also be able to help you there. Otherwise, I think there's a question right there.
Just try to install GPUArrays on the Mac OS.
Mm-hmm.
And is there a technical reason why OpenGL is not with the backend?
Oh, that's because the OpenGL backend is very recent as well. It's on my branch. So that should be added soon when I have the time to clean it up and merge and tag. Okay. Yes?
How does, for the transpiler part, how would the OpenCL and OpenGL backends differ in how they would implement things?
So they have a different set of intrinsics. Sadly, I don't really know why.
like adding two vectors, is one more performant?
Would be, of course, the compilers differ, so I guess there will be differences, but in most of the code it should be minimal. And with OpenGL, there are a lot of things you can't do simply. So it's much more restricted in the computing sense. But for a few simple broadcasts, it works pretty well, I guess. And yeah, I still need to benchmark it thoroughly. I just recently added it, and I'm pretty curious as well how it will turn out. It might actually work better in some cases because OpenGL is a bit more high level and takes away a bit of control from the compute, but that also means that they probably do optimal decisions about some of the things where if you write pure OpenCL or CUDA stuff where you can mess up as a programmer. So I'm pretty curious. Yeah, and then the whole how you write a kernel is quite different in OpenGL. It's a very weird API because it's bolted on the compute. It's, yeah. It tries to do the same stuff as in the graphics API, but then somehow puts it out to another buffer. That's basically how it works. Yes?
Do you have any plans to support WebCL?
Well, does WebCL have the plan to be supported? It's probably the first question. I don't know, the last time I researched, it still was kind of not very well supported across browsers.
I think with regards to WebCL, the other problem is it's running a browser. So it's sandboxed, and so you can't actually access this from a native Julia version. So before we can talk about that, we need to talk about running Julia on top of JavaScript, which is a proposition that has been talked about, but there's no real effort because too many dependencies of Julia itself don't run well on top of JavaScript. And for performance reason, one might not actually want to do that.
Did anyone actually get JuliaBox running?
Yes,
oh,
2 people.
That's not too bad.
As CUDAnative right now supports clean memory transfer?
No, currently not.
So the question was if CUDAnative.jl supports peer-to-peer memory transfers between multiple GPUs, and currently it does not.
Oh yeah, that would be nice.
Currently it does not.
Shouldn't be too much work to add. It's just calling more of the API, but we haven't done so far.
Okay.
Good.
Okay.
Let's wrap.
Yeah. You want to wrap?
Okay. We are still going to be around, but I don't think we need to keep it as an open forum. So enjoy your early break, and see you during JuliaCon.